Okay, thanks everybody for joining us. It's our great pleasure today to have Alexei Onatskiy presenting a paper on the trace test for high-dimensional cointegration. And our panelist today is Bykhovskaya. Alexei, the floor is yours.
Thank you very much for inviting me, and thank you very much for joining this talk. I'm going to talk about a joint project with my longtime co-author, Chen Wang, who is at Hong Kong University. The title of the project is Trace Test for High-Dimensional Cointegration. So it says here on the slide, preliminary and incomplete. In fact, it's complete now, but still preliminary. So, well, please interrupt me at any point asking questions or trying to clarify things. So I will start from a picture. And so this is just an illustration. It's not very serious application. What you see on this picture is 25 time series of detrended logarithms of employment data in 25 biggest sectors in United States. This data is taken from NIPA tables, and actually table contain like more than 60 sectors or around 60 sectors, but I took 25 largest ones as of 1948, which is the first year in the series. The data is annual. It starts in 1948, and my sample goes up to 2001. It's actually the same sample that Dushan-Bai used in his 2004 paper when he analyzed non-stationary data using a factor model. So this data is also slightly tampered with, in the sense that I wanted you to see well the dynamic of each of the series. So I shifted each of the series so that they are separately seen on the graph. So they are not the mean, but actually intentionally mean is different. Now, so if you run Dickey-Fuller tests here, so this series look like they're non-stationary. But my question would be, how would you test that there is no cointegration here, or maybe there is cointegration here? In fact, it's probably quite obvious maybe that there is cointegration here. But again, I'm using this data just for illustration, because what I will be talking about is the test for no cointegration. And the test for no cointegration, there are many of tests available. And usually what you would do if you want to test no cointegration in some multiple time series, you would be writing down this vectorized regression in error correction form. It will be multidimensional. In my case, the dimensionality n is 25. Then, well, you might want to include lags, several lags of x variable on the right-hand side. You will also include some deterministic terms. It may be mean and maybe trend, maybe quadratic trend, maybe something like that. And I'm putting this in this regressors dt, and there is this error term. And then you may use Johansson's likelihood ratio test for no cointegration, which is equivalent to testing that this matrix is equal to 0 against an arbitrary number of cointegrating relationship. It can be 1, it can be 2, it can be n, it doesn't matter. And if you have this kind of null and this unrestricted alternative, then the likelihood ratio test, and again, you're conditioning on initial observations. So then the likelihood ratio test, which Johansson described, has this form of so-called trace statistic. You basically taking logarithms of 1 minus lambda, where lambda are some eigenvalues that I will be describing shortly, summing over all these eigenvalues and then multiplying by the temporal size of your data t and take minus sign. And if the statistic is above critical level, you're rejecting. Now, these lambdas, as I said, are eigenvalues. They can be interpreted as some squared canonical correlation coefficients between the changes in the variable x and lagged level of the variable x. And squared canonical correlation coefficient is just multivariate generalization of usual correlation coefficients squared. So you take this product of four matrices. In fact, if dimensionality is 1, then this will be simply basically the usual squared correlation coefficient between these two random variables. But since the dimensionality is n, you have matrices instead. So this is an n by n matrix. Then take eigenvalues of this matrix, and these are lambdas. So that's what you would do. However, it is very well known that in moderately large dimensions, the test that Johansson proposed will not work. So the reason for that is that the critical values of the test based on the asymptotics, which treats n as being fixed. In this particular case, it will be fixed at 25, but number of time periods is assumed to go to infinity. And if this is the case, then likelihood ratio trace statistic will converge in distribution to the trace of a matrix which is represented in this form of integrals, which are matrices themselves. Here for B is multidimensional, 25-dimensional Brownian motion, and F is just transformation of this Brownian motion. Precise form of this transformation depends on the specification of error correction model, like which deterministic terms you include there, but it's not particularly important. Important thing that as t goes to infinity, indeed, you can simulate this distribution. You can find critical values, and such simulation actually were done for relatively small n. You can find them in the textbook up to n equal to 12. However, in our data, t is 54. I only have 54 years of data, and 54 is slightly more than twice n. It's kind of big stretch of imagination to say that t goes to infinity, but n is being fixed when t is just twice the size of n. So we know that in this kind of situation, test severely over-rejects no cointegration hypothesis, and this is very well documented. Some early papers, Hoyne, Sorensen, and Gonzalez and Pitarakis, but since then there were tons of studies that confirmed this over-rejection phenomenon. And there were proposed several solutions a long time ago. One of them is Bartlett correction. And this solution is basically takes this asymptotic distribution and scales it so its first moment better matches the finite sample situation. And then the hope is that after the scaling, the other moments of asymptotic distribution also match the moments of finite sample distribution well, but there are no guarantees, of course, of this, because this is just simple scaling. And another solution is bootstrap, but bootstrap in this kind of situation was only made with relatively small dimensional systems in mind. Okay, so this probably will not work for n equal to 25. So what are we doing in this paper? In this paper, we're considering this double asymptotics when n and t go to infinity proportionally, so that their ratio converges to some number in between 0 and 1/2. The reason to have here 1/2 is that if c is bigger than 1/2, then the likelihood ratio statistic will not be well defined, because some eigenvalues of that matrix that I showed you will be exactly equal to 1. And when you compute logarithm of 1 minus 1, you will get logarithm of 0, which is not well defined, and everything will break down. So we will only consider case when this ratio converges to something in between 0 and 1/2. And we will show that in such asymptotic regime, the trace statistic, when appropriately centered, and we will tell you what center is, and scaled, just divided by n, it will converge to normal distribution. There will be no need of any Brownian motion, of any transformation of Brownian motion, nothing like that. It will be normal distribution with some particular mean and some particular variance. This mean and variance can be explicitly computed, and we get explicit expression for this mean and variance. These expressions are quite complicated, but relatively elementary. You can program them on MATLAB and tabulate. So, and we give in the paper table for different values of C. This mu and sigma only depend on the ratio of n over t. And then, of course, you can use, for example, two-sided test for null hypothesis of no integration by just comparing with critical values of this normal distribution. And we also provide some Monte Carlo evidence supporting very good size properties of the test. And we have some interesting findings with power that I hope I will have time to show you. So this is basically what this paper is doing. Now let me tell you what is new relative to my own previous work with Chen Wang, because we were working on this topic for quite some time, and we wrote a couple of papers where we showed that if you consider empirical distribution of these lambdas, then it will converge to so-called Wachter distribution, which in principle can be indexed by this C. Here is the density. Remember, C is the ratio of n over t. Here is the density of this Wachter distribution. It's elementary density. The distribution is located, it's supported on some compact interval with boundaries B minus and B plus. These boundaries have very simple relationship to C again. So this distribution is easy to simulate, it's easy to operate with. And in particular, this convergence to Wachter distribution implies first order behavior of likelihood ratio statistic. So it says that if you divide likelihood ratio statistic by n times t, it will converge in probability to the integral of minus logarithm of 1 minus lambda with respect to this measure. Like I just need to multiply by the density of Wachter and take integral. This will be first order behavior. What we are doing in this paper, we are going from first order behavior to the second order behavior, because we are no longer interested just in the limit. We use this limit, by the way, in previous work to propose alternative Bartlett corrections, but we didn't propose test. So here in this paper, we will be proposing tests based on the fluctuations of this statistic around this limit. Moreover, actually, we derive more general central limit theorem for any statistics of this particular form. It's sum of functions of lambda, where functions are relatively good. They should not have singularities in some open region, which includes this support of Wachter distribution. But otherwise, this can be any function. For likelihood ratio statistic, this function has very special form. It's minus logarithm of 1 minus lambda, but it can be anything. So, well, you can devise your own test based on different statistic, not necessarily likelihood ratio one, and get the asymptotic normality from our paper. Now, there was another work, and it's Anna's work with Gorin, and there are 2 papers by now, and they consider also test not just first order behavior but second order behavior, but not of entire empirical distribution of lambdas, but of the largest several largest eigenvalues. It can be actually even growing number of eigenvalues, but not proportionally to n or t. In the simplest version of maximum eigenvalue test is also likelihood ratio test of the same null of no co-integration, but against alternative of only one co-integrating relationship. There are other versions of maximum eigenvalue test, but let me consider just the simplest one. In this case, likelihood ratio statistic has this form without any sum, right? It's just minus t times logarithm of 1 minus the first eigenvalue, lambda 1. And under simultaneous asymptotic, Bykhovskaya and Gorin show that if you center and scale appropriately this statistic, and you see that there is weird power in the scaling appearing here, then this object converges in distribution to solve. I'm sorry. Just 1 second. I don't know what's happening in this in that place, but there was terrible noise coming from the speakers. I'm really sorry about that. It's beyond my control, but hopefully here it's okay, right?
Yes, perfect.
Okay.
Thanks.
Thank you very much. I'm sorry. So this Tracy-Widom distribution appears a lot in random matrix literature, and you can think about it as, for example, distribution of scaled and centered largest eigenvalue of a sample covariance matrix of IID noise, for example, IID Gaussian noise. The method that Bykhovskaya and Gorin are using is based on really path-breaking finding that these lambdas are well approximated by eigenvalues of so-called Jacobi ensemble of random matrices. So you can think about this as matrices which have this multivariate matrix beta distribution. And they use this approximation to get this result. Unfortunately, the approximation is not quite exact. There is some error of this approximation, not because of imperfection of the method, but it's genuine error of the approximation. And it is not enough to study the trace statistic. It is, though, enough to study the maximum eigenvalue statistic. So our methods in this paper are totally different from methods of Bykhovskaya and Gorin. Okay, so in the rest of my time, I want to split my presentation into 3 parts. First, I will be talking about setting. It will be very simple setting and our main result. Then I will show you more fundamental result and will describe very briefly general proof strategy. How do we prove things? And finally, I will show you a lot of pictures with Monte Carlo. Okay, so setting will be super simple, and it's super simple like on this slide, but if I'm making it slightly less simple, I will not be able to do anything. So it's important that it is simple. So in this setting, I have vector autoregression of order 1. And the only deterministic term that I'm including in this vector autoregression is constant gamma. Okay. Well, and I also require that my errors here are IID normal, but the variance-covariance matrix of this IID normal can be arbitrary. The test will be invariant with respect to this variance-covariance matrix, so it's not really big deal. What is big deal is the number of lags. Bykhovskaya and Gorin in one of their paper allow for more lags than one. I cannot do it here with our methods. Now, I'm testing null that pi is equal to 0 against alternative that pi is not equal to 0, and consider modified Johansen stress statistic. Why is it modified? It's modified in the same way as Bykhovskaya and Gorin modify the maximum eigenvalue statistic? Well, basic modification comes from the following thing. Instead of considering canonical correlation between change in X and lagged level X, we detrend lag level X with particular detrending method. We take last observation, subtract the initial observation, divide by the total number of observation, and this is our coefficient on the slope on the trend. So and well, that's the only modification, but other than that, the statistic is exactly the same as before. So let me now show you a little bit technical slide. I want you to show why this detrending is crucial for me. So technicality in this slide will be mostly in notation. So first 3 bullet points is notation. Delta X would be matrix of those first differences of X. And X minus 1 will be matrix of those detrended lags of X. Okay, so I have this matrix is delta X, X minus 1, and this eta is the matrix of errors, like composed of the, each column will be error time t. Now let L be t vector of ones. So if you consider identity matrix minus L prime divided by t, this is just a projection on the space orthogonal to like constants. And finally, in my definition, U will be upper triangular matrix of ones with zeros on the main diagonal and below. Okay, so I'm finished with notation. And then remember, I'm interested in canonical correlation between demeaned delta X and demeaned and after detrending X minus 1. So demeaning means simply that I'm multiplying this delta X by this matrix M. Remember, M is matrix which projects on something orthogonal to vector of ones. So multiplying by M means demeaning. And here I'm also demeaning this X minus 1. So I'm interested in canonical correlation between this thing and this thing. But then simple algebra shows you that this thing is nothing else as eta, it's errors, multiplied by M. And this thing is eta multiplied by M times U, and then again times M. And this is all I need because this matrix is M, and M times U times M are very good matrices. They are circulant matrices. And circulant matrices are all simultaneously diagonalizable. And this simultaneous diagonalizability is playing a huge role in what I'm doing. If I'm not able to simultaneously diagonalize, my method will just not work. So why simultaneous diagonalizability is good here? So remember, the eigenvalues that I'm considering are eigenvalues of this product of 4 matrices. And this matrix is actually just kind of simple covariances and cross covariances between this and this. So if I simultaneously diagonalize this stuff, then I will be getting 4 matrices of very, very simple form. So this eta tilde will be discrete Fourier transform of the original etas at all fundamental frequencies. Okay, so it's eta tilde is Fourier transform of my noise at all fundamental frequencies. This matrix D is diagonal. It's matrix of eigenvalues of this matrix. Of course, D star D is also diagonal. D star is also diagonal. There is nothing here. So I have very, very simple matrices now. And moreover, the element in this diagonal matrix D, which stays in the first column and the first row, is equal to 0, because see, I'm demeaning my data. So at 0 frequency, the spectral density there will be 0 because I demeaned everything. And this actually explains why in my later formulas, I will have not T, but T minus 1. Because although there are T fundamental frequencies, frequency at 0 will not play any role because I'm demeaning stuff. So in all future formulas, instead of t, I will be using capital N, which is t minus 1. So with this slide over, I can now relax a little bit because this is most kind of technical slide. And the point again was that I need this demeaning to be able to simultaneously diagonalize things. Okay, so now what is the main result? Main result is like this. Consider this simultaneous asymptotic regime. Then you need to center likelihood ratio statistic by the following thing. So it's n times t times something which depends only on this object c hat, which is the ratio of n and t minus 1. Okay, and this object is nothing else, is something describing first order behavior of the likelihood ratio statistic that I already showed you. It's integral with respect to Wachter distribution of this thing, except that Wachter distribution here is indexed not by C, but it's indexed by this C hat. And you can remember this Wachter distribution has very simple density, so you can explicitly compute this integral, and it has this form. So this is my center. Now this mu and this sigma also unfortunately should be expressed in terms of some contour integrals, with contour encircling all like the domain where this Wachter distribution lives. And this integral takes logarithm of 1 minus z and multiplies by some functions, mu and sigma here, which I derive explicitly what these functions are later in the paper. But you cannot analytically really say what this mu c and sigma squared c is. You need to switch on your computer and compute things, just evaluating numerically the integral. Okay. And that's my main result. Now, just a few comments. First comment is about this this enigmatic table of critical values of Johansson's test. So if you look at different textbooks, then depending on dimensionality of your data, you will find critical values which look outlandish, extremely outlandish. So they're first start well, but then they go to, I don't know, some very strange numbers. Well, this previous result actually is basically saying that if you divide everything by n squared, then everything will simply converge to 2. So all this kind of strange numbers is nothing else as basically 2 multiplied by n squared. And well, this is just fun part of this thing. Now, how the centering this thing look like? Its combination of logarithms, not quite clear how it behaves, but it behaves very simply. So it only depends on the value of the c hat. Remember, it's n divided by t minus 1. Well, if it is small here, it's close to 0 if c hat is small, but then if c hat converges to 0.5, this converges to some finite number here, and the slope becomes actually infinite, but it touches the axis here, so it's behaved nicely. Now, how the sigma and mu behave, and again, this is numerically computed, mu and sigma, there is nothing erratic in their behavior. They're behaving very well. So mu for most of the values of c is basically 2. Well, it fluctuates around 2 a little bit, but as c approaches 0.5, both sigma and mu explode. They are not touching this axis at all. So they're going to infinity. And well, so that's something that I can say analytically, of course. Okay, and now let me come back to that picture that I showed you when I began presentation. So remember those log employment data. So how would I use the test for this log employment data? Well, first of all, n is equal to 25, t is equal to 54, and I will first compute c hat. C hat is 25 over 53. It's below 0.5. Everything is fine. It's 0.47. Then I will compute this centering thing. And for centering thing, it's, combination of 3 logarithms, so you can easily compute it. It's number like that. Then I will look up mu and sigma from the table. It's tabulated, or like MATLAB code is provided, so you can compute it for yourself. And finally, I'm just computing the usual, well, slightly modified, right? The trace statistic. It has this very, very big value, 2,811. And then I'm simply, well, just computing this, this normalized trace statistic, which turns out to be 27. Standardized by subtracting mu and dividing by sigma, you're getting this 6.31. And now you need to use just usual two-sided test, right? You should compare this with 1.96 by absolute value. And critical value, or sorry, p-value here will be really 0.000000. It's 10 in the power minus 10. So it's really rejecting the null of no cointegration. Now, interestingly, the maximum eigenvalue test, which Anna proposed with Vadim, so it has p-value, which is 0.68 here. And I should confess that I tried a couple of data sets before this, because their test works extremely well. And this data was the first that I showed, or that I found that their test doesn't have really power, and I will later show you why. So this is actually related to the fact that the ratio of n to t is pretty close to 0.5 in this particular context. But trace test works here. Well, again, one more time stress, it's not intended as criticism of their test, because for most data set it will work extremely well. But for this particular situation, it doesn't. Now, where the power of the trace test comes from. So what this
Alexei,
figure shows, yep.
May I interrupt you briefly
Yep.
about the previous example? Do
Yep.
you have pictures with how the entire eigenvalues look like? My guess it may be also because the true rank pi here is large, so that there are actually a lot of co-integrations.
Yeah, so here how they look like.
Okay.
So what you see here is Wachter QQ plot. So on the horizontal axis is quantiles of the Wachter distribution, which is a limit of the empirical distribution of eigenvalues under the null of no co-integration. So if there were no co-integration, you would expect the eigenvalues be along 45-degree line here, because on the vertical axis it's empirical quantiles. Okay, it's this kind of eigenvalues basically. So they should be along this red line if the all of them eigenvalues behave according to the null hypothesis. But here, most of them, all of them are larger actually. And you are right that it's probably saying that there is a lot of integrating relationship there. And it is also consistent with the finding by Dushanbe, who found that there is one non-stationary factor in this data. If there is one non-stationary factor, which explains all stochastic trends, then there will be basically n-1 co-integrating relationship there, right? It's exactly when the maximum eigenvalue test will not work well, because it's not one co-integrating relationship or two co-integrating relationship, or let's say 5 co-integrating relationship there, but it's almost everything is co-integrated because there is one stochastic trend. Well, I'm not sure that there is one. According to Dushanbe, well, there is one factor which is non-stationary in this data. So I presume that maybe that's the reason. But basically, the power of the test comes from the fact that all eigenvalues, each of them, is kind of above the diagonal. If you look at the largest eigenvalue, there is no much room for fluctuation for the largest eigenvalue, although this is a little bit deceiving, because remember, you are taking the logarithm of 1 minus this eigenvalue. So logarithm of 1 minus eigenvalue will stretch the fluctuation of the largest eigenvalue, but turns out not to be enough here to reject the null of no integration for test, which is just based on the fluctuation of the largest eigenvalue. Okay, so that's where the power comes from. Now I want to say a few words about more fundamental result and a general proof strategy. And this will not be very long. By more fundamental result, I mean the central limit theorem for statistics of this form, where like this function f doesn't need to be logarithm of 1 minus lambda, but practically anything. And so our proof is trying to mimic a proof of the behavior of this kind of statistics for lambdas, which are eigenvalues of simple covariance matrix. And this proof was given in By and Silverstein in 2004 Annals of Probability paper. So relative to their paper, what is difficult for us is that they only have one matrix to analyze, but we have product of 4 matrices to analyze. So the method is substantially extended to handle that case. But whenever possible, we tried to just mimic what they were doing. Sometimes it was not possible, then we kind of introduced new stuff. So, but the main idea remains the same. The main idea was like that. To analyze fluctuations of this kind of statistic, you need to focus on fluctuations of so-called Stieltjes transform of the empirical distribution of eigenvalues. What is Stieltjes transform? It's just a very simple thing. It's like this. You take in all eigenvalues, subtract complex variable z, and take 1 divided by this eigenvalue minus z, sum everything, divide by n. So this is called Stieltjes transform or empirical distribution of eigenvalues. Now, this is a function. So I will be looking at the behavior of this function along some contour in the complex plane, which encircles the support of the Wachter distribution. So I will derive basically functional central limit theorem for this function. And then I will be using complex analysis, which says basically if I integrate this Stieltjes transform multiplied by a function f along this contour, then what I will be getting is the sum of the function evaluated at this particular singularities. Well, singularities of this m are happening at lambda 1, lambda 2, lambda 3, etc. So Cauchy theorem tells us that this integral will be really just be equal to the sum of this values of the function evaluated at lambda j, well, and then I scale by n. So linear spectral statistic can be well expressed as contour integral of this Stieltjes transform times this function. So all that you need to derive CLT for any linear spectral statistic is to know the functional central limit theorem for Stieltjes transform, and you will be done. So our main result is basically to find the behavior of this Mn over some contour. The first order behavior, of course, is simple. It's just integral with respect to Wachter distribution. But the second order behavior, which I will be looking at, is this. I will be looking at this Stieltjes transform as a function over this rectangular contour, and we'll be deriving basically functional central limit theorem. So that's what the paper is doing. Now, the main result is as follows. Under the null hypothesis, a truncated version of this centered and scaled Stieltjes transform viewed as a stochastic process on the contour converges to a Gaussian process with mean function mu and covariance function sigma. And this mean function mu and covariance function sigma is what you've seen in the main theorem under the contour integrals when I was computing those mu c and sigma c. And I told you that you need to take integral of logarithm of 1 minus z times some functions, which I will later develop. And these are these functions. These are mu and sigma. And we obtain explicit form of these functions, but it is a relatively complicated explicit form. So you still need to use numerical procedure to describe this this function if you want to plot graph, for example. Okay, and now what is the, well, I told you I will derive functional central linear, but how will I do that? Well, the key tool, which is used again and again in this paper and also in the paper by Zidong Bai and Jack Silverstein, is as follows. So here, remember, we are analyzing eigenvalues of this product of four matrices, and then build the Stieltjes transform of those eigenvalues. Now, these four matrices, I already told you, were related to Fourier transform of the data under the null. It's simply this this noise, Fourier transform of noise, and there will be this diagonal matrix D. Unfortunately, of course, Fourier transform are complex valued things, and this diagonal matrix is complex valued. There will be complex valued things there. So I want to make everything real valued. So instead of complex valued Fourier transform, I will be considered real valued Fourier transforms. And this comes at a cost because diagonal matrix become block diagonal with blocks 2 by 2 blocks. Okay, and if I'm doing this, these epsilons now become real sine and cosine Fourier transforms of the noise, and delta will be block diagonal matrix instead of diagonal matrix. And I will call this matrix C, this D, this again C transpose, and this A. Well, more explicitly, this C can be written as sum of this kind of quadratic expressions where this is not quite a vector, this epsilon j, it's two vectors. It's two columns of matrix epsilon, two adjacent columns corresponding to sine and cosine Fourier transform. So this is rank 2 matrix. It's not rank 1 matrix, but then I'm summing over all j going from 1 to n over 2, and I'm assuming here that n is even. If it is not even, then one block in this delta will be 1 by 1 instead of 2 by 2, but this will not change anything. It's just awkward that there are odd and even numbers. So I will assume that there are only even numbers existing. So so all these matrices C, D, and A have this form of sum of rank 2 matrices. And then what is being done in all these calculations? One of these epsilons is knocked out of the consideration. You just cross it, you forget about it. You put 0 instead of it. And you get new matrices, C tilde, D tilde, and A tilde. And compare them to previous, to full matrices like C, D, and A. And this comparison is made using some matrix algebra. But then this comparison ultimately leads some equations which describe the behavior of all objects of interest for me, including Stieltjes transform. So the main tool which I'm using, I'm knocking out epsilon 1 by 1 and comparing the transformed thing with the original one. So that's the tool, but I'm not telling you exactly what I'm doing. So what exactly I'm doing the following thing. The strategy is simple. First, you want to analyze fluctuations of this object. So you split this object into one, which is just m minus its mean, and the other, which is deterministic objects. It's mean of M minus this centering M. So first step is to split this object into stochastic part with mean 0 and deterministic part. And I will be analyzing this thing separately. So this thing is analyzed as follows. Remember this epsilon 1, epsilon 2, these are not quite columns, but rank 2 matrices, 2 columns. So imagine now that I'm conditioning on epsilon 1, epsilon 2, etc., epsilon j only. Let me call this conditioning mean as ej, right? And then I can split this difference between M and unconditional mean into these differences between conditional means with increasing information, right? From j minus 1 to j, from j to j plus 1, etc. This is just algebra. But the thing is that this now is martingale difference, which I'm summing. And I can use CLT for martingale differences. One such CLT is in Billingsley book. I'm specifically using theorem 35. And the difficulty there, the only difficulty in applying this theorem is that I need to find the limit of these conditional variances of each of these martingale differences there. And for that, to find that limit, I will be using this knocking out epsilons and comparing them using some linear algebra and coming up with some equation which will describe me this limit. Okay, and next, what I will need to prove tightness, because remember, I'm not just after finite dimensional distribution. I'm after functional central limit theorem. So I will need to prove that the tightness of this process, and that was. Actually, we obtained a lot of these results maybe several years ago, but then we were stuck. And the key that opened to us things was Anna's and Vadim's paper, because that closeness of lambda to the eigenvalues of the Jacobi ensemble, because actually for tightness of this thing, you need more or less smoothness of this process, like along the contour. But the process behaves very potentially not smooth close to the real axis, because sometimes this lambda, the eigenvalues, can come close to the contour with very small probability, but close to the contour. And then in the Stiltiès transform, remember the lambda minus z is in the denominator, and z can be anywhere on the contour. If lambda is close to the contour, then lambda minus z is almost 0, and I'm divided by 0, and things exploding all of a sudden. So we were not able to prove tightness, but Bykhovskaya and Goring results allowed us to some machinery which we used to prove some large deviation inequalities for this eigenvalues, which was enough to show that with overwhelming probability the process is tight, and that's all that is needed there for the functional central limit theorem. And finally, I'm analyzing this deterministic part, and while deterministic part is a different story, I'm first deriving some equation which is satisfied by this expected value of M. Then I'm comparing with equation which should be satisfied by my centering constant, and look at the difference between two equations and analyzing that difference. When I'm analyzing that difference, I'm again using this tool of knocking out epsilons and comparing with results without knocking out of epsilons and with knocking out of epsilons. So it's a long process, unfortunately, so which I cannot really describe very quickly here. So, but let me now show some nice pictures. So first picture, what you see here is the Monte Carlo size of our test. On the horizontal axis is dimensionality n, and I consider all kind of different dimensionality t. So the dimensionality t will be encoded in c hat. Remember, C hat is basically n over t, is n over t minus 1, right? N over t. And I'm considering 6 different values for this C hat. I'm starting from very small ones, 0.05, then 0.1, 0.2, and then they increase to 0.3, 0.4, and 0.45. And then I'm just looking at how size of the test behaves when n changes, but t is kept proportionally to n, so that we are on the same C hat, right, schedule. So we see that, like, even for very, very small n, like 4, the size of the test is not that bad. It's oversized, but it's 8% at worst, right? But once things become like, I don't know, n is 25, so it's already smaller than 6%, which is pretty good. And then it converges for whatever C hat is to the nominal size, which we were quite impressed. And this is a quite precise Monte Carlo. The standard error of this Monte Carlo is very small, because we get a lot of repetitions of Monte Carlo. So now let me show you advantage relative to the Bartlett corrected test. Remember, I told you that one of the solution to this over-rejection was proposed by Johansen himself. So he proposed just to Bartlett correct thing by dividing asymptotic distribution by some constant. And what you see here is the size of Bartlett corrected tests for different C again. On the top panel, it's Johansen's proposal how exactly to Bartlett correct the test. So let's focus on this picture here in the top left corner. When C is very large, as in my example here, Bartlett corrected test is just really bad thing to do. Its size is kind of almost 1, like almost immediately when n increases. Even if when C is 0.3, it's still pretty bad thing. But when C is smaller than that, like 0.2 and smaller, here I'm showing you a scaled version of this size, just for you to see better. Well, it starts at 0.05. It's good, but then it becomes undersized when n increases. So it's just goes to 0 eventually. But well, for reasonable like applied data, maybe when C is less than 0.2, Bartlett corrected test is not that bad. It looks pretty good in terms of size. Now, like Chen and myself proposed different Bartlett correction, and this is just the same with different Bartlett correction. It behaves much more stable, but still unsatisfactory with like real big distortions of size, but not actually for very small C. For very small C, this Bartlett corrected test looks okay. And in our case, it doesn't converge to 0. It kind of stays at 0.05. So again, this happens again, sorry. I don't know whether you hear it, but there is huge noise in the room. Well, anyway, so this is the size of Anna's and Vadim test, and there are 2 versions of the test that they propose. One is using so-called Johnstone correction, and the other is without correction. And well, it converges to 0.5, a little bit slower to my taste, but it's okay. It's doing its work, and without correction for relatively small values of C, it's actually doing very well. It's converging to 0.5 here, maybe slightly slower than convergence of the trace test. Now, what about power? To analyze power, I'm using this very simple model. Again, it's the model that I consider, but matrix pi will be diagonal matrix with some coefficients non-zero. I will call them raw, and all of them will be exactly the same raw. And there may be k of them not zero. If there are k of them non-zero, then there are k co-integrating relationship in the data. Actually, diagonal nature of this matrix is without loss of generality, because I can multiply both sides of this equation by any matrix from the left. So it's not necessarily diagonal, but here it's easier to understand with diagonal thing. And my raw will be varying from 0 to 1. Yep.
Sorry, just to remind you, there's 5 minutes left.
Yep. So the time, I will finish in a couple of minutes. Okay. Okay, so that's how power of our test look like when we increase raw. Like 0 raw is almost, it's null hypothesis. Raw bigger than 0 is further and further away from the null. And we see this weird behavior of the power. It's non-monotonic. The test power increases, then decreases back to the size, and then goes to 1. And it depends, power also depends on how many co-integrating relationships we have. If there are many as the number of series, then the power is increasing to 1 pretty fast. But if there is only 1, the power is, no, not very good. Now, why is this non-monotonic behavior? We just look at how eigenvalues of this matrix behave. There are 25 eigenvalues, how they behave as I'm changing raw from 0 to 1. And it turns out that they first dip a little bit and then go up. So this means that actually the reason why test rejects the null first is that all distribution of eigenvalues go below, and then it starts to go above. But it's very nonlinear process. So had I used one-sided test, I wouldn't have power at all from the very beginning, and it will be actually even inconsistent test. So, but well, because I'm using two-sided test, it happened this hump-shaped thing. So, well, this is comparison with power of Anna's and Vadim's test. If the true number of co-integrating relationship is 1, their test is here dashed line, have bigger power than trace test. If the number of co-integrating relationship is as many as the number of series, their test has lower power. And right picture here correspond to one-sided test. So let me skip this. And my last slide is showing how this power changes when C, remember C, the ratio of N to T is increasing. So here C is very small and power is super. But when C starts to increase, power becomes pretty bad actually. And it's really kind of not going to 1 anywhere here for the whole range of raw for C as large as in my example that I showed you. But still, it was enough for me to reject the null of no co-integration there. And that's basically all I have to say. Thank you very much for your attention.
Thank you so much to our speaker, Alexei Onatskiy, and to our guest panelist, Anna Bykhovskaya. So I'm going to stop the recording now, and we can move to the question and answer part.